Let's start lecture 26. The course is corrosion protection methods. We have been discussing on the effect of environmental factors and associated corrosion protection. And we are discussing effect of chloride on passivating metals. So we saw two aspects. One is effect of chloride on the change in transpassive potential, as well as we have also seen the effect of chloride on the change in I passive, which is the current density corresponding to the passive zone. Now, we have to also see the effect of chloride ions on the I critical, which is the current density corresponding to the extreme point in the active passive anodic part of a metal. Now, let us look at that aspect. So, if we see chloride ion effect, we have seen the plot looks like this. This is E volt log I, let us say ampere per centimeter square. This is the anodic part of active passive metal. So, what will be the influence on the concentration of chloride ion? As we increase the chloride ion concentration, okay. So, this potential corresponding to ET, transpassive potential. This point is I passive, this point is I critical. So, I critical goes up, I passive increases, transpassive potential decreases as we increase chloride ion concentration. So, that was the observation. Now, we have understood the effect of ET as well as IP due to the presence of chloride ion on the corrosion rate of the active passive metal. And in both the cases, we have seen that chloride ion actually degrades the metal and the corrosion rate increases. Now, we have to also see what could be the way we have seen that the I critical increases and what could happen to the active passive metal if I critical increases. Now, if we look at the mixed potential theory and corresponding anodic plot of active passive metal, let us say this is E volt log I ampere per centimeter square. So, this is the typical anodic part of active passive metal. Corresponding points are IP, I critical, and this is ET. And we are looking at, so we have seen three aspects. One is on ET, we have done it in our previous class. On IP, that is also discussed in our previous lecture. So, we are looking at on I critical and corresponding corrosion rate, influence or effect on corrosion rate. So, we are looking at this point. So, now if we have chloride ion, let us say this is for the condition of no chloride ion presence. Now, if we have chloride ion, the graph would move towards forward direction. So, let us say it moves like this. Okay. This will be the pattern of the active passive anodic part of the metal. Now, I critical has moved to this location. And what is the importance of I critical? So, I critical is the maximum point in the active passive anodic part before the metal achieves passivity. Now, as per mixed potential theory, let us say this is the cathodic part. So, this particular polarization is corresponding to IC, it is the cathodic current density. Okay. And corresponding point is E cathode, E equilibrium for cathodic, and this is I naught for cathodic reaction on the metal surface. This is the reduction process that is going on. Now, these two plots, that green one as well as the black one, if we consider, these two plots are there, and as per mixed potential theory, an unique potential is achieved where the total rate of cathodic reaction is equal to total rate of anodic reaction. And since here we have a very simple system where one single anodic process, which is metal dissolution. So, let us say this actually indicates metal dissolution, and this indicates reduction, or we can say oxidant plus Ne equal to reductant. So, this ox and red is nothing but oxidant, or in brief it is known as ox, and reductant, in brief it is red. An oxidant example Fe3 plus, O2, copper 2 plus, even hydrogen plus, and reductant Fe2 plus, H2O, or even OH minus, copper, hydrogen. So, these are reductant. Now, for in case of hydrogen, if we consider, this would be written as, okay. So, this reduction process is going on. Now, since it is only a single reduction and single cathodic process and single oxidation or single anodic process, and we have to see where we are finding a point where both the anodic and cathodic reaction rates are same. And in this case, the green line, which is the polarization line for cathodic reaction or cathodic process, has crossed the I critical. So, this particular point, if you see, it has crossed it. So, once it crossed it, and I could see that this is the point where IC is equal to IA, and IA is nothing but anodic rate, and IC is nothing but cathodic rate. Okay. Now, both these processes would try to, as if like try to push each other towards this point. So, that means for the cathodic process, the potential will drop to this particular point, and for anodic process, if it's starting from here, which is corresponding to E equilibrium for anodic process, and this is I 0, which is exchange current density for the metal 1 on metal surface. Okay. So, these two equilibrium potentials, they will be taken to this potential, which is E core. Fine. So, now you could see that the anodic process is having anodic polarization, and the over voltage would be this much would be over voltage, and for the cathodic process the over voltage amount is this much. Okay. So, we could see that the potential is dragged to this point where total rate of anodic rate and cathodic rate, those two are equal, and the potential is lying in between these two extreme equilibrium points. Now, this is the concept we follow in case of mixed potential theory. So, if you want to understand more on this, please look into the mixed potential theory, what has been explained in our previous lecture series. Now, for this kind of situation, as the potential of the anodic part is dragged to this value to this value to this value, so it will not go like randomly like from here to there. It will follow this track. It will follow this track. It will follow this track. Similarly, for the cathodic one, it will follow this track. Okay, and then it goes to meet both of them and meet at this point where I critical, which is corresponding to E core, and there is that is the mixed potential, and here total rate of anodic and cathodic processes are same. Now, since this anodic part going through this track, okay, so it has to first cross this extreme point, which is I critical, that point needs to be crossed. So, in this case, because the cathodic line is away from, which is not touching the I critical, and it is on the right side of I critical, it will follow this track and reach to E corrosion without any problem. Fine. Now, this situation would have been different had it been the cathodic process cuts like this particular line, if it is the cathodic process. If it is then this, then I am seeing that 3 locations I meet the mixed potential theory. One location is this one, another one is this one, another one is this one. In that case, the system would like to stay at this point, at this location. Okay. So, the system would not reach to the I passive, because in case of point corresponding to this, I have E core as well as the corrosion current density would correspond to IP, which is the passive current density, which is very low, and the system will achieve passivity. So, for the case, in case of the blue line for the cathodic process, green line for the cathodic process, definitely I will achieve passivity, and the anodic line will follow the red line and then reach to mixed potential. But in case of brown line, this particular case, the system would not be able to achieve passivity, because it is not crossing the I critical. So, this particular line, it is not crossing this particular point. Okay. So, this I critical point. So, it will not achieve passivity. So, what will be the polarization response if you want to do a dynamic polarization? So, in case of this E core as well as I core, the typical plot pattern would be like this. Okay. So, this is for E core, and I can draw this line. This is IP or equal to I core, corresponding to green and black lines. Now, when it is brown one, that case the polarization plot would look like this. This is for the brown and back lines. Fine. So, this particular situation is called cathodic loop. So, that would not achieve a stable passivity and system will fluctuate. So, this is not good for the metal. So, it would remain at this location, So, this is my E core and this will be my I core, which is corresponding to this point, fine. So, which is a very high rate of dissolution. And you could see that all those 3 points junction between the black and the brown one are actually having similar IC, that means the cathodic current density, and same anodic current density. And all 3 points we meet the mixed potential theory, but the system would remain at the lower potential value or this potential value because the system is trying to achieve passivity. So, then it would remain there. But if we forcefully take it upward, the way we do in case of polarization study in the laboratory scale with the help of potentiostat, that time I can get this kind of plot, fine. So, it is very important that the cathodic line should cross the I critical point. If it does not cross the I critical point, and if we start with a fresh metal, that means it does not have any passive layer on top of it or oxide layer on top of it, and then definitely the attainment of stable passivity would be better in case of the situation where cathodic line crosses the just bypasses the I critical value. Now, interestingly, coming to the situation where we have chloride ion, so which is the blue one. So, let me just remove those brown curves so that it becomes easy for us to explain. Okay. Now, this blue one corresponds to having chloride ion. So, that is what the entire anodic plot has moved towards the right and I critical has gone up. Now, if we consider the same green line as the cathodic reaction or cathodic process that is going on, I could see that though it bypasses the I critical for the black one, with the what is the that is the condition corresponding to no chloride ion, but that one would not cross the or would not bypass the I critical when there is chloride ion. And definitely in that case stable passivity would not be achieved, just like how we have gotten the cathodic loop. Here also we will get cathodic loop because I could see mixed potential can be possible at these 3 locations where the total rate of cathodic process reaction as well as anodic reactions, both these reaction rates are same, or other way we can say I cathodic equal to I anodic at those 3 locations. Similar like what we have received, what we have obtained in case of the brown line cutting the black line, and we got a cathodic loop when we did polarization study. So, that means in case of presence of chloride ion, I could see that the I critical moves towards right, and if the same cathodic process is going on, I will not get any passivity. So, for that is bad for the system, and for active passive metal our primary interest would be to achieve passivity, so that the metal remains inactive or the rate of dissolution would be so low corresponding to I passive. Okay. As we see that I passive is nothing but the I core, but that would not be achieved. So, that means it is definitely affecting the metal corrosion rate, and the corrosion rate would go up enormously. Okay. So, that is the disadvantage of having chloride ion for the corrosion of metals and alloys. So, now question is, in this case we have seen that the IP is also changing. So, that means it is a combined effect, but we can assume that this particular line can actually move towards, it can remain same as let us say other factors are not changing, ET remains same, IP remains same. Only thing is I am seeing that I critical, I see this I critical is going up. So, that means the plot would be like this. So, I critical only the pink one, the pink line corresponds to only the effect on I critical. This is a kind of hypothetical situation, only I critical is enhanced, IP does not change as well as ET does not change. So, then again also at that case also I could see that I will not be able to achieve passivity, because the cathodic line corresponding to cathodic polarization would not take the metal to the I passive zone, because before that it has to cross two points, which is this point, and system would not be able to reach to I passive. So, this is affecting the corrosion resistance of the metal badly, because we have a very high corrosion rate corresponding to this particular I core. And if we see this I core and I core, had it achieved passivity, there is a huge increase in corrosion current density, and this is the case with chloride, and this is chloride ion is absent. So, this is what we wanted to explain, why chloride ion affects the passivity achievement or passivity attainment in case of active passive metals, and this affects negatively. That means passivity attainment would be difficult. So, now coming to the protection part, if we have active passive metal and if we somehow get rid of chloride ion, definitely I will not have such situations. I can easily get passivity corresponding to passive zone or the I passive. So, removal of chloride ion helps attainment of passivity Okay. So, this is one way for the protection. Okay. You remove chloride ion. So, that is what we initially said, that if we remove corrosives or the ions which help corrosion. Okay. So, this is one protection, that is what it is better to remove chloride ion. For example, in some cases you cannot remove chloride ion. Okay. For example, if you are using a system with where metal in seawater application. So, that chloride ion of course will be present, but the situation where there is a possibility of removal of chloride ion and there is a system where chloride ion presence even in a small amount would affect the corrosion rate hugely, or rather increase the corrosion rate or avoids or prevents passivity attainment, that case it is better to remove chloride ion. Fine. So, now let us look at one more instance where we talk about removal of oxidizer. Or oxidant. And what are the strong oxidant? Let us say Fe3 plus. So, if we consider HCl, an iron container is there. So, this we have iron container, then HCl, if it is impure, when it is impure, that time we can have Fe3 plus little bit, a very small percentage of Fe3 plus. What could be the influence? We can explain this with the help of mixed potential theory. So, now we can draw a plot between log I and we know that if it is dilute HCl, iron does not go to passivity, and let us say this is deaerated HCl. Deaerated means dissolved oxygen is not there. So, the condition is we have HCl, we have Fe3 plus and no oxygen. So, that case it will follow active dissolution and the iron would not show any passivity. So, this is my anodic plot for the iron dissolution, and let us say this is my cathodic plot when we do not have Fe3 plus. So, this potential is E equilibrium for hydrogen reaction, let us say cathodic, and let me put it hydrogen. So, this corresponds to H2. For that case, this is my equilibrium. Depending on the concentration of H plus, this potential will be decided. Let us see, let us explain this. We have been talking about E equilibrium all the time. Let us see what is the importance of this or how it appears. In fact, for these you can also follow earlier lecture series. Now, for hydrogen reaction, this reaction I can write the Nernst equation like this. Okay, so this is the equation I can think of where, and this is temperature is 25 degrees Celsius, 1 atmosphere pressure, and where E naught H plus half H2 equal to 0. So, E equal to nothing but minus 0.059 pH. Now, if we maintain pH at 0, so then this value would be equal to E naught, and this value is the equilibrium line, equilibrium potential when the pH is 0. If pH is 1, then E H plus half H2 would be equal to minus 0.059 volt. Okay. So, this is my equilibrium potential, and how it appears? Because when we talk about hydrogen reaction, when equilibrium achieves, this rate and this rate both are same. So, IC equal to IA, and IC is given a negative sign because this particular direction of current we are talking about, that direction of current is opposite to IA, and when these two are equal, so I can say IA, if I consider the magnitude, that become I naught, which is the exchange current density. This is exchange current density. Fine. So, now when we achieve this equilibrium, that time there is no net gain of hydrogen gas or there is no net gain of H plus ion. So, that is basically a non-corroding case situation. Non-corroding means the corrosion is a constant loss of metal, but here why it is we are saying non-corroding, because there is no net change of hydrogen ion or H2 gas or H2 molecule. Okay, so that's what it is, non-corroding condition, and it also corresponds to equilibrium. So that's what we are always writing, that equilibrium and this junction point where cathodic and anodic half cell reactions for hydrogen reaction meets. Okay, so this is my reaction corresponds to H this, and this is basically nothing but H plus plus E equal to H. Okay. So, we have anodic process and cathodic process, and this is for single half cell reaction where you have cathodic as well as anodic process, and this particular point corresponds to I naught for hydrogen, and always the reaction happens on a metal surface. So, that is the metal, and here it is iron. So, I can put it as iron because on iron surface hydrogen evolution takes place, and this corresponds to E equilibrium for iron, and this corresponds to I naught for iron on iron surface. And as per mixed potential theory, when we do not have Fe3 plus, then the potential will be taken from, this is my E core, this will be taken to this value, this will be taken to this value, and they will meet at this point, and corresponding point is I core. Okay. I could see that the corrosion rate of iron follows that particular rate, which is I core. Now, if we add Fe3 plus. So, Fe3 plus is a strong oxidant, and if we consider the standard reduction potential for hydrogen as well as Fe3 plus to Fe2 plus. So, E naught Fe3 plus to Fe2 plus, its value at 25 degrees Celsius and 1 atmosphere pressure is 0.77 volt, whereas E naught hydrogen is equal to 0 volt. This is the standard value. So, that means I could see that Fe3 plus electron equal to Fe2 plus compared to H plus E equal to half H2. This one Fe3 plus has got a much higher reduction ability compared to H plus ion, and this potential also, equilibrium potential also lies above E naught H plus slash half H2, and every time we are talking about reduction potential. Remember, our convention always remains reduction. Now, if we have Fe3 plus and Fe2 plus, this Fe3 plus going to Fe2 plus, that reduction process can happen, and where it would happen? It would happen on the metal surface, which is nothing but iron, and this potential also lies above it. Depending on the concentration of Fe3 plus and Fe2 plus, this particular potential or equilibrium potential as per Nernst equation equal to E naught Fe3 plus Fe2 plus RT. Since we have one electron, so F, which is 1 Faraday, ln concentration of Fe3 plus divided by concentration of Fe2 plus. Okay. So, depending on the concentration of Fe3 plus and Fe2 plus, I would have, this is my equilibrium potential. Okay, equilibrium potential. So, now this equilibrium potential lies above this potential. So, when it lies here, let us say it is lying at this location. So, what happens? I think still I will have problem to draw it. Let me say it is lying here. Now, it will have its own polarization. Okay. So, when we do that polarization, this is basically corresponding polarization for Fe3 plus going to Fe2 plus, and the current density corresponding to Fe3 plus Fe2 plus. So, let me just put it as IC Fe3 plus. Okay, the cathodic current density corresponding to polarization of Fe3 plus going to Fe2 plus. As per mixed potential theory, before it crosses this anodic line for the iron dissolution, and here iron dissolution is taking place. This is the anodic part. Fe minus 2 equal to Fe2 plus. If it experiences another cathodic process, so in order to fulfill the mixed potential theory, which says that the total rate of reduction process should be equal to the total rate of anodic process, and here we have two reduction and one anodic process or one oxidation process. So that means this line corresponding to this which is the equilibrium potential for the hydrogen evolution reaction. So when the polarization happens for Fe3 plus to Fe2 plus, it experiences another cathodic process. So it is to be added up, so that we can have a mixed potential where the total rate of reduction, that means the IC corresponding to hydrogen evolution and IC corresponding to Fe3 plus reduction, these two, if we add it up, that current density should be equal to IA for the iron dissolution from the iron plate. So it comes and then it adds up there. It adds up and then follows the trend. So this line is nothing but IC total equal to IC for hydrogen evolution, IC for, this is IC for hydrogen evolution, this is IC for Fe3 plus reduction. So this is the total, and this particular line corresponds to IA iron dissolution, and this is the junction point where the rate of total reduction process is equal to the rate of total anodic process. So this will be my new mixed corrosion potential, and this particular point would be I core. Okay. Now we could see that when we have iron presence, Fe3 plus presence, and since it's a strong reduction oxidant, so it has a higher ability to get oxidized. So that time I could see the current density where it was, there was no Fe3 plus, no Fe3 plus, and where we have with Fe3 plus, the current density goes, it actually increases, and this increase is happening because of the presence of oxidizer. So now if we can remove oxidizer, which is Fe3 plus, definitely I will have benefit of very low corrosion rate, which corresponds to this point, which is the corrosion rate corresponding to no oxidizer. So that's why removal of oxidizer helps for active metals. Fine. This also has influence on the passive metal, so we'll talk about that. In fact, presence of oxidizer actually helps in achieving stable passivity instead of going for active dissolution mode. So we'll talk about that part in our next lecture. But if we consider only the iron Fe3 plus, of course we are not putting this other reaction. So this reaction is this. So this is my E equilibrium Fe3 plus, and this is IC Fe3 plus on iron surface, because this reaction is also happening on iron surface, and this is nothing but Fe2 plus minus electron equal to Fe3 plus, which is oxidation reaction or anodic process for the single half cell reaction, which is nothing but Fe3 plus slash Fe2 plus. So now we could see that if we remove oxidant, just like what we have given this example, let us say iron 3 plus, we can actually reduce corrosion rate, or other way it enhances corrosion resistance. And remember, this is valid for active dissolution of metal in a corrosive. Now, active dissolution of metal, what do I mean by that? It's basically the polarization lines, polarization lines are all in the active mode, or active polarization is followed for anodic process. Okay. So, that is the condition that if we remove oxidant, we can avoid corrosion rate of the active metal. Now, similarly, let us say if we have copper plus ion in iron pipe or iron tank. So, this copper plus has got a higher reduction ability, fine. So, now if we consider copper plus, if that ion is present, it can take 2 electron, it can go to copper, and this copper can deposit on the metal surface because it has higher reduction ability. So, this is iron, let us say, and now what happens, this copper is acting like a cathodic site. So, if we have oxygen there, this cathodic reaction would happen this reaction can happen on those small cathodic part, and then for this reaction close to that copper deposit, anodic reaction or Fe minus 2E equal to Fe2 plus, this anodic process would happen. So, that the dissolution is localized wherever that copper deposit is happening. Because of this localized nature, it leads to peating. So, now again if we remove copper ion, definitely it would be helpful, because those copper deposit cannot happen, and immediately we will have the avoidance of such localized peating. Now, this is also a serious oxidant. Why? Because E naught copper plus copper is equal to nothing but 0.34 volt, whereas E naught Fe2 plus Fe is equal to minus 0.44 volt. So, we could see that copper ion is a serious oxidant. So, if we remove oxidant like copper ion or iron ion, Fe3 plus ion, then we can actually reduce the corrosion rate for active metals. And here active metal means the metal follows activation polarization and not going to the passive state, or it does not show any active passive behavior in that particular very medium, fine. So, their removal of oxidant can help, and it can lead to a better corrosion protection, or we can have a very low corrosion rate. Now, we will also have a situation where actually presence of oxidant helps in achieving a very low corrosion rate, and that relates to active passive metal. So, we will discuss that in our next lecture. Thank you.